Hello everyone, welcome to the 8th part in the series on how to create your very own multicolored research-based code playing program. So finally, in this video, we would implement multicolored research playouts. So the traditional way of doing this, the playouts are meant to be random, but in our case, since we've provided some basic heuristics, our playouts will be based on that particular heuristics. And by the end of the playout function, what we need to do, we need to say who won that kind of a playout, so whether it was won by black or won by white. And usually, the way to go would have been to count all the territories and then take into account Kami, taking into account captured stones, and know the result. But calculating all that is a little bit too expensive, so we want to make it faster. And since the playouts are quite random still, semi-random, but yeah, we'll go for a trick that would help us to improve the performance. So assuming the nature of the heuristics that we have, the heuristics would be given us a position with almost 1 point based territories for each site. In very rare cases, we'll be having dead groups that are not killed yet. So those 1 point territories would be filled with the stone relative to the site to move, and those dead groups, although they should have been removed, but again, doing all that is possible, but that's very expensive, like from the CPU power perspective. So we would be just filling the liberties with random colors there, and generally we might find a scenario where, let's say, we have a group, a DAG group of, say, 5 stones. There won't be DAG groups like 100 points tracking. That it's not going to be like that because the heuristics is not ended up with those positions. Yeah. So say around 5 stones DAG group, and for that DAG group, we would just either fill some missing liberties with white stones or with black stones. It might happen that the DAG group suddenly becomes a living group, yeah, but well, anyway, the DAG group would not be killed, so that would be treated as a living group, but it would not affect much the overall results, and even if it does, so these are kind of a semi-random playout, so we're not taking a decision based on just a single playout. We will be making many playouts, and generally, even not taking much care of those groups is not affecting the overall result. Usually, does not affect the overall result that much. On the other hand, since the heuristic is quite stupid, although it's fast, it might happen that there could have been a living group, but due to stupidity of heuristics, that group would die. But again, because of this kind of thing, that we would leave that as is, this means that maybe that group could survive. So it's a source of randomness for playouts. Meanwhile, the playouts are directed by a certain type of heuristics. I don't know whether what I've just said makes sense to you guys, but this is just the very simplest possible way of implementing things, and I will be using this as a placeholder because I want to build the actual multicolored research as soon as possible to get the very first results, and then I will come down, and from there on I will be able just to incrementally improve some parts of the code, thinking about performance, thinking about the heuristics, thinking about the playing strength, thinking about all the things in the world in regards to this engine. So yeah, let's implement the playout routine today, and within the next 2 videos, hopefully we would end up with the multicolored research itself, and then we'll be able to have a look at how the basic multicolored research implementation is going to be working. Okay, so without further ado, let's get started. So I'm going to open the source code from the previous part. So I've moved the heuristics header a little bit. So now we have within the heuristics we have not only the gen move but also the random move and the code to search for the smallest group, the smallest target group. while the not suicide is left within the board section here. So here we have the board section. Okay, so just a change of a layout, nothing much about that. Okay, and also we want to have a new section in our code, so I just copy this one, and this will be multicolored tree search. So here I would like to define the structure called multicolored tree search. For now this is going to be empty. It will contain a tree node later. For now it's going to be empty, but I'm using it because we would be associating methods related to multicolored research with this kind of structure, so that's the reason why we need to define it now. So I'm creating the function which would be the part of this multicolored research family. So multicolored research points to multicolored research structure, and the function is called playout. It will be taking board pointer to board, the pointer to the board structure, right? And it would be returning the integer, either 1 if black wins and -1 if white wins. Okay, so with this in mind, we can get started. So we should have a function that would determine when the game has ended. Usually the game has ended when either there are no moves on board left, or whether there are both sides has made a pass move. And tracking that is possible, but again, we want this to be as fast as possible, and we don't want to spend processing power for those things. So I would go a very naive way, but it seems to be working nicely so far. So again, this can be changed in the future. Again, I just want to make this as quickly as possible, and then go in for improvements. Okay, so we would be deciding whether the game is ended or not by the number of moves, and usually within the 1,500 moves, assuming the current heuristics. Again, this is just assuming the current heuristics. You might be wondering why the move number is so big, but within the around 1,500 moves, the position is settled. In most cases, there would not be territories that do not belong to anyone. There still might be dead groups, but yeah, the board would be filled, and the territories would be most of the territory points would be like one point surrounded by 4 stones of a given color. We'll be printing the board along the way, so hopefully this is going to be clear. So I'm defining the move number here. This is going to be equal to 0. And I also want to define the variable called stones, and this would be the slice of type float 64. Here we would be storing, so empty is not used, just for easy and simpler indexing. So this would be the number of black stones, because black is a constant of 1, and this would be these would be the white stones, because white is a constant of 2. So if stones indexed by black would go here, stones indexed by white would go here. Okay. Now we are making an infinite loop here. Well, not very infinite, yeah. So for, I mean, this is like a while loop syntax, but in Go we use for. We don't have while in Go. In Golang. So for move number is less than 1500. So before this has happened, what we do, we generate a move. So move is equal to board gen move, and we do board site. So whichever site it is now, we generate move for that site. And then, regardless of whether the move is legal or not legal, because if the move is not legal, it's not going to be made on board anyway, so we don't care about this. And since we don't care about passes as well, we can simply say board play, and then we do the move and the board site. So again, if the move is okay, it would be played. If it's not okay, it would be just skipped, and another move would be tried. And also want to say move number plus plus, so we increment the move number here. And after this, very simple, I just want to say board.show. So want to see how the board after the playout has been completed essentially looks like before we start any countings. Okay, now here I don't want the GTP loop being activated. I just want to say Monte Carlo tree search equals new Monte Carlo tree search like this, and I want to say Monte Carlo tree search and playout, and that's it. So we just compile and run. So go build and go. Okay, stones declared but not used, missing return, undefined Monte Carlo research. Oh my goodness. What have I done? What have I done? First of all, this is going to be like this. And then let's fix all the issues I've just created. So yeah, we don't use stones for now. So this is okay. Not using stones for now. Missing return. Let's return 0 for now. 385. And that's because I need to assign the value. Okay, not enough arguments. Yeah, we need to send the board as an argument here. We'll be doing lots of copies of board and would need to have some separate functionality for that sake, but that will be covered within the next series. So this is the board position after the playout has been completed. And like I've been mentioning, we have this, so one territory, 1 point of territory, 1 point of territory, 1 point of territory, mostly. In this case, we don't have DAG groups. So in this case, we can just fill this 1 point territory with the color. So this one is surrounded by black, so it would be filled by black. This one is surrounded by white, is going to be filled by white, etc., etc. We also might encounter a situation where there would be some DAG groups, in particular. It's not like, yeah, like this one, for instance. So this group is entirely dead. Okay. So it might happen that this one would be filled with white, and you might think that this is a DAG group that would not survive. So it's not really that great to count it as a living group. But again, these are the semi-random playouts, so we don't care much about being that precise. Okay, because mostly like the result, the difference in scores would be quite big, so this is not going to affect the game result that much. Okay, so yeah, let's now try to score things here. So the playout itself is kind of completed now, and from here we can start our scoring. So we loop over all of the board squares. So square is equal to 0. Square is less than board size multiplied by the board size. And square plus plus. So if board position indexed by the square is equal to off board, we just continue. Then, if board position indexed by the square is equal to empty, so here we might encounter two scenarios. So the first one, we want to fill the liberty of own color. Otherwise, we do the random fill up. Okay, so we want to know what's the color of the color that surrounds an empty point of territory if it's within the diamond. So we have a diamond function which checks the up, down, left, right stones relatively from the current square. So color is equal to board diamond, and we pass square here. So here it might happen that the color would be either black if the given square is surrounded by black stones. It may be white if it's surrounded by white, and it might be zero. If it's zero, it means that we are dealing with a empty square that is attached to a dead group, most likely, or this is no one's territory. This is very rare. This should not happen really, but anyway. So if color is not equal to empty, this case the color is either black or white. Then we do board position index by the square is equal to color. So we just fill in our eyes with the color that we have. And also want to say stones indexed by the color plus plus. So we count the stones. Now we also need to uncomment stones here. Okay. But it also might happen that the color is empty. And in this case, we just create a random color. So the random color is going to be equal to rand int number 2 plus 1. So this would be either 1 or 2. This value for the random color would be either 1 or 2. So we do board position index by the square is equal to a random color. Okay. And stones stones indexed by the random color would be equal to, just increment that. Okay, so this was the case if the board position was empty. Otherwise, the board position is not empty, which means it's a stone, either black or white stone. So we simply may do stones indexed by the board position indexed by square. So the stone value at the board position, either white or black, so respectively stones are getting populated. Okay, after this, we can show the board again. So board show. Now we are going to see hopefully no empty squares. Okay, so this is the position, the end result of the position. So for instance these stones are obviously dead. So essentially white should be like plus 4 points. So then it actually is that it's counted here. So yeah, let's just print the fmt print line and want to print stones. Yeah, let's consider another example here. So 190 stones for black and 171 for white. So it means that black wins the game. But again, say here, so we have this is a dead stone, this is a dead stone. So this means that the real result is 190 minus 2, and this one, and white would be 171 plus 2. Okay, because these would be like otherwise these stones would be white. Okay, but again, this 4 squares, so 190 minus 171 plus 4 squares minus 4 squares, this is not that crucial really. Yeah, because the difference is usually quite a big. Assuming the level of the kind of randomness of the heuristics itself, it's quite it's still quite random. Again, this is a dead stone, but this is treated as if it's black's piece of territory or stone. So definitely this approach might have downsides in terms of being precise, but again, since even random playouts are used in multicolored research, then literally this could be any position, any really. And since we have at least some heuristics, still we have the bias towards a more likely the real outcome of the game, at least at the level of that heuristics. So at this moment, I think this is just fairly enough to have this like implementation. So we have no empty squares, and we can now calculate who's better. Okay, so let's do some final calculations, and essentially we will get done after. So we create the result variable, which would be equal to stones indexed by black minus stones indexed by white, essentially all black stones minus all white stones. But we also want to give the kami to whites, so we do plus 7.5, assuming Chinese rule counting, plus 7.5, yeah. And we also need to normalize this score. We can also print the result now. So result, and now we know that, so minus 2.5 means that white wins by 2.5. And by the way, what about that groups? Yeah, in this case we don't particularly have that groups. We? Yeah, we have. Oh, well, this is interesting. So since these stones are white and they are treated to be like territory points, so if not these three stones, that black would be the winner of this game. And now it turns that white is the winner of this game, which feels a little bit unfair. But again, we have many playouts, so it doesn't matter that much. Let's have a look at another results. Yeah, 53 points, 0.5. So the gap is huge. Okay, minus 86. The gap is huge. Okay, so black wins by 41.5. Okay. White wins by 134. Okay. White wins by 24.5. So usually the gap is quite big. Okay. By 5.5 by black. Yeah, so, well, again, just as a placeholder for now, I think this should be just good enough. And also we need to bear in mind the fact that we need to, assuming the multicolored research, we need to normalize the results. So we want either 1 if black wins or -1 if white wins. So we can do the following. So if the result is greater than 0, this case we return 1, and otherwise we return -1. So positive score means black 1, so return 1. Negative score means white 1, return -1. We cannot have a score equals to 0 because of the kami 7.5, so this would be at least half a point, like more than 0 for any site. And we don't need this return anymore because this will always work. So greater than 0 and otherwise would be means that white 1. So okay, and yeah, we got another playout. Yeah, we're not printing anymore 1, but we can actually do that. So what have I done? Yeah, we don't need this board show anymore. We can do only this one. Yeah, essentially we don't need this either. Well, okay, we can just let's get rid of this. Like this, and right. Let's make sure that nothing is printed at the moment. So we'll print debugging stuff in here. So result equals to the playout, and I want to say board.show and fmt print line and result and 1. Okay. Okay, so black 1. Okay, looks to be the truth. Yeah. White 1. Interesting, yeah. Visually, it's not seen that nicely, but probably, yeah, probably. We don't know by how much. We don't care by how much because the algorithm, multi-colored research algorithm, only needs to win or loss. White 1 here, yeah. Probably white 1. So yeah, these are the playouts. Returning 1 for if black wins, and returning -1 if white wins. Okay, so this is it from my side. Thanks for watching. I'll see you next video. Until then, and cheers.